Okay, I'm going to do, I think, 2 more short lectures in this week. I'm not covering things completely, but I'm giving you now some highlights from those first 7 chapters of Thinking Strategically. In particular, in the book, a very important chapter comes, well, a little bit later from the notion of the prisoner's dilemma being resolved. It's chapter 5, the discussion of strategic moves. An anonymous statement to highlight this, right? I used to think I was indecisive, but now I'm not so sure. By review, we're, again, trying to predict the likely outcome of these games, of these interactions. We know the general lesson from looking at sequential games is to look forward and reason back. We further note that simultaneous games, of course, are really all about simultaneous best replies. We learn that there could be no equilibria in a game. So that means that we need to identify now the meaning of mixed strategies. That gets us to the topic of strategic moves. Consider the game of employee monitoring. All right, employees can work hard or they can shirk. Give them a salary, let's say, of $100,000 unless they're caught just shirking. Suppose the costs of their effort are $50,000. Now the managers can decide to monitor or to not monitor. Imagine that the value of employee output is running at $200,000. The profit if the employee doesn't work is 0, and the cost of monitoring is $10,000. What you note then is if the game involves the manager who decides to monitor, the employee might decide to work or to shirk. If the manager decides not to monitor, the employee could decide to work or to shirk. The underlines indicate the optimal responses to each of the other players' strategies. But the best replies in this game do not correspond. That means there's no equilibrium in what we could say pure strategies. There's no dominant strategy. There is further no dominated strategy. So how would the players behave? The mixed strategy analysis indicates that some of these games are going to be unreasonable predictors of a one-time interaction. They are going to be, however, predictors of long-term proportions. So what we're going to do is learn how to calculate mixed strategies, look at how they operate in practice, and modify our particular example a little bit by way of a cost increase. Suppose we're dealing with the penalty shot and the game-winning goal. The penalty kick in the Pee Wee League version involves shooting right or left by the kicker. The goalie, of course, can attempt to block right or left. Making the wrong choice by either side indicates a loss. Kicking right when the goalie has jumped left earns us the point. Kicking right when the goalie jumps left earns us the point. It turns out there are no mutual best responses. It seems that there's no equilibria. So we need to figure out a way to play the game. What we want to know is what proportion of the time should we be kicking left? What proportion, therefore, right? So what would you know? What would you do if you knew that the goalie were always jumping left? Then you would, of course, shoot right. Back off of that and say, well, what if it's not really always blocking that direction? But maybe the goalie attempts to block by jumping left 75% of the time. In probabilistic soccer, we'll allow the goalie to randomize. We'll say that the goalie jumps left P proportion of the time. And now we want to know what is the kicker's best response. We know that if P equals 1, the goalie always is jumping left, let's say, and we know that we should kick right. And if the proportion equals 0, that means the goalie always jumps to the right, so we know we should kick left under such a circumstance. Now those are the 2 endpoints, but probabilities run between 0 and 1. The kicker's expected payoff is, in general terms, the result of them kicking left, which would be -1 times the probability that the block is to the left, plus 1 times 1 minus the probability that the block goes left. The math to that yields 1 minus 2p, and furthermore, kicking right yields the value 2p minus 1. So I should kick left if basically the proportion of the time of blocking is less than 1/2. Right? If they have a tendency not so often to go left, then I should go left. Now, I should kick right if the probability P blocking right is greater than half. Sorry, blocking left is greater than half. If they have a strong tendency to block to the left, I should kick to the right. And I'm indifferent if they mix at the point of 50-50 jumping left and right. Furthermore, what's the value of P that's best for the goalie? We know that a value P isn't a good idea because the kicker just is going to shoot and the goalie loses the game. Furthermore, a P equal to 0 doesn't make sense because, again, the kicker shoots in reaction to that and we lose the game. If I were to go 0.75 to the left, right, they shoot to the right and we lose the game half the time. If I were to assign P of blocking at 0.25, the kicker will shoot to the left. And I'll, on average, lose the game half the time. And now what we do is we have, let's say, 55% chance of P. That means the kicker shoots right, and I have a 10% chance of loss of the game. So, right, the probability 50% this is causing the kicker strategy to be kind of a toss-up. They're not sure which they should do. See, so the randomizing of left and right jumps to block generates the best possible payoff from the goalie's point of view. Mixing strategies, there's the lesson. Right? If the opponent knows what I'll do, I'm going to lose. So randomizing takes away an ability to know what I'm going to do, and therefore I'm not going to be taken advantage of. You have to make your opponent indifferent between your strategies. Here are some strange implications. A player chooses the strategy to make the opponent indifferent. If you're doing this right, the other player earns the same payoff from either of the strategies that they attempt. So the commandment that results from this strategic moves chapter is as follows. Use a mixed strategy that keeps your opponent guessing. Go back to employee monitoring. Let's say the employee can choose to shirk and work with the probabilities P, so that if shirking happened 20% of the time, working would be 1 minus P, let's say in an example, 80% of the time. The manager will choose to monitor Q probability or not monitor 1 minus Q probability. Maybe that's 50% chance monitor, 50% chance of no monitor. First, you find the payoffs expected for the employee from a pure strategy. If they were to work, they receive 50. Their profit from work is 50 times Q plus 50 times 1 minus Q. So basically, they're going to get a profit of 50. If they shirk, they receive 0 or 100. Remember, they could get caught under monitoring. Their profit from shirking is 0 times Q, which is the probability, the proportion of the time that the managers monitor, and we presume that shirking is caught, right? Plus 100 times 1 minus Q. The rest of the proportion of time that there is no monitoring taking place. So if I shirk, profit from shirking is 100 minus 100Q. Next, you calculate the best strategy for the possible strategies of your opponent. For example, if monitoring were to happen less than half the time, I should shirk, because the profit from shirking is actually going to be greater than the profit from working. And if monitoring happens more than half the time, then I should work, because now the profit from shirking is less than the profit from working. At the point of Q, monitoring exactly 50-50, that makes somebody indifferent because the profit from shirking is equal to the profit from working. So I know from the point of view of the manager, employees are going to shirk if my monitoring occurs less than half the time. So to keep the employees from shirking, I must monitor at least half the time. And our monitoring strategy is being used to obtain the employees' payoffs. Remember that there's that interdependence. So managers think, okay, I can monitor. The monitor best response runs 90 times 1 minus P minus 10 times P. And not monitoring 100 times 1 minus P minus 100 times P. So for the probability of shirking less than 1/10, we wouldn't really need to monitor. For any probabilities of proportions of shirking above 1/10, it makes sense for the manager to monitor. Precisely at 1/10 of the time, shirking, then we've made managers indifferent. So this is an iteration process that eventually discovers that the shirking working proportions are shirking 1/10 of the time, and the monitoring proportions wind up in equilibrium being half the time. So the mutual best response is identified in the model. Now we can identify the equilibrium payoffs, but they are rooted in the probabilities that are those exact mixes of working versus shirking lined up against the mix of monitor and no monitor. How does this work in real life? Of course, it comes up in sports, football, tennis, baseball, racquetball, and so on. It occurs in law enforcement, where we'll issue traffic tickets on a probabilistic basis. It works in the case of price discrimination, where airlines are using standby policies. It's being applied in policy compliance when you see companies doing random drug testing. It also works in anti-terrorism practice, such as under rules of random passenger checks. Let's change the cost of monitoring to $50. Remember, before it was $10,000. Now the cost is $50. The new scenario, of course, is what would make the employee different. You can try this on your own, identifying the change. Take in those probability-based formulas anywhere you see the $10,000 monitoring cost and just switch it to a $50,000 monitoring cost and interpret what you see happening. In terms of IRS audits, there's also a mixing strategy that occurs. There was a 1997 study that looked at offshore evasion. And as a result of the research there and the data, the IRS decided to calibrate some random audits. Commissioner Charles Rossetti in 2002 began to note that audits had become much more expensive. So the number of audits decreased slightly. And as a result, the offshore evasion picked up, we'll call, and increased to a little over $70 billion additional offshore evasion. So you see, as the audits get more expensive, you have to increase the budget to keep the number of audits constant. Consider the case of parking lots. Increase in costs to one party shouldn't really change the optimal mix for that party. Ticketing rate in the parking lots, let's say, could be adjusted. Here, imagine a 10% increase in enforcement costs comes about. Should that be responded to, met with, by decreasing enforcement? So you'll reduce the ticketing rate. As a result, the incidence of illegal parking increases. In law enforcement, you attempt to motivate compliance at lower monitoring costs. So you have to identify the optimal audit probability, the drug testing mixing strategy, the parking ticketing strategy, and of course always figure out if the punishment fits the crime. Here we see something that's crucial. What do we mean when we say the term random? A study found, for instance, that a 15% chance of being stopped at an alcohol checkpoint deters drinking and driving. Implement it. Set up checkpoints 1 day a week. 14% probability, because 1 day out of 7. Then select Fridays. That's going to be an exploitable pattern, unfortunately. So that might not be truly random at that level. You have to use a mixed strategy that keeps your opponent guessing. And your probability of each action has to be the same from period to period. So what does an exploitable pattern look like? Imagine the managers who engage in their monitoring strategy half the time. What has to that thus mean is that there would be a 50% chance of monitoring taking place every day. You can't set up a pattern of monitoring every other day. It turns out, though, humans are very bad at creating these mixes of strategies. And they have to get good at not having patterns arise, because people will exploit patterns. So that's a key lesson in the Mixing Strategies chapter. So put this one up on Blackboard now too.